Okay, so good evening, everyone. As you know, my name is Rahul. So this week I will talk about Laplace transform. Okay, so from the definition it says if ft is a function, if ft is a function defined defined for all t greater than or equal to 0, so the Laplace transformation of ft into capital Fs is as below. Okay, so it says Laplace of function ft will be limit, not limit, integral 0 to infinity ft e raised to the power minus s time t dt. Okay, and when you integrate it, it will become function of s, and here you have to be very careful. Here it is a capital F. Okay, similarly, okay, inverse also exists in this case. Okay, so and the inverse Laplace transform is given by that will be ft and will denote inverse of Laplace, capital F of Fs. Okay, and since we can see that if Laplace exists, which means that inverse of the Laplace also exists, which means that I can also write what I can write inverse Laplace of Laplace of ft will be nothing but ft. Okay, and similarly Laplace of inverse Laplace, and here you can see this time it will be capital F, and this will be nothing but fs. Okay, so this is the definition of Laplace transform, and here there is a condition s is greater than 0. Okay, so we can see that this is the definition of the Laplace transform. Okay, so now we will take one example. Okay, suppose let we have a function ft equal to 1. Okay, when t is greater or equal to 0, then find fs. Okay, so in this case what we will do is we will just substitute this ft equal to 1 in this equation. Okay, then we will get fs. So what is fs? Fs will be nothing but the Laplace transform of ft. Okay, and in this case you can see it is nothing but the 1. Okay, so it will be 0 to infinity 1 times e raised to the power minus st dt. Okay, so it's a very simple definite integral. Now you can see that from the definition of integral we can write e raised to the power minus st 1 divided by minus s, and the limit will be 0 to infinity. Okay, so the Laplace transform of 1 will be when you put the limit. So you can see that when the limit, I mean upper limit, when it goes inside this, so you can see that it will be nothing but the 1 by infinity, which means that it will be 0, minus when you put 0 it will become 1. So in this case it will be 1 by s. Okay, so it is a very simplest example. Okay, simplest example for the Laplace transform of 1. Okay, now let's take another example. Okay, suppose we have ft equal to e raised to the power at. Okay, then we can see what will happen. Okay, when t is greater than equal to 0. Now we have to find Laplace transform in this case. So you can see that it will be nothing but Laplace of e raised to the power at, and simply you can write 0 to infinity e raised to the power at multiply e raised to the power minus st dt. Okay, so we can write e raised to the power. Now here there is a condition. I will tell you what is that. I can write like this. Okay, now if s minus a, okay, is greater than 0, then we can write like this. Okay, 1 divided by minus s minus a, and this will be s minus a. Okay, t I left it. Okay, so now we will put limit 0 to infinity, and you can see that it is nothing but 1 divided by minus s minus a, and when you put the limit it will be 0 minus 1. So simply it will be 1 divided by s minus a. Okay, so this is the second example. Okay, here you can see that I can write, I can put this limit when s minus a is greater than 0. When if s minus a is less than 0, we cannot write like this. We cannot, because when s minus a is negative, then if you put the limit, upper limit, it won't become 0. Okay, so that's why we have to put this condition. Okay, this was the second example. Now we will go through some rules. Okay, that is linearity of Laplace transformation. Okay, so what does it say? It says Laplace transformation of a times of ft plus b times of gt, it will be simply a times of Laplace transformation of ft plus b times Laplace transformation of gt. Okay, so this is the property, we have to use it. Okay, now we will take another example, that is third example. We have to find Laplace transformation of cos of hyperbolic cos, okay, at. Okay, and in the same scenario we will also find hyperbolic sinusoidal function of at. Okay, now we have to use one Euler formula, that is nothing but, we know that hyperbolic cos of at, it is nothing but e raised to the power at plus e raised to the power minus at divided by 2, and in this case hyperbolic function of at will be e raised to the power at minus e raised to the power minus at by 2. Okay, now you can see that if I take Laplace transformation of hyperbolic cos of at, then from the linearity property I can write 1 by 2 outside, and Laplace transformation of e raised to the power at plus Laplace transformation of e raised to the power minus at. Okay, so 1 by 2, and previously we saw that Laplace transformation of e raised to the power at was nothing but 1 divided by s minus a. Okay, and in this case it will be s minus, and here you can see that at the place of a it is minus a. Okay, so it will become 1 by 2 1 divided by s minus a plus 1 divided by s plus a. Simply it will be 1 by 2 s plus a plus s minus a divided by s square minus a square. Okay, so a will be cancelled out, and with this 2 and here it is a 2s, it will become s divided by s square minus a square. Okay, so this was the Laplace transformation of hyperbolic cosine function. Okay, now we will see what will be the Laplace transformation of hyperbolic sinusoidality. Okay, so it will be very similar, but there is a change. Here you can see that here it is a negative sign. Okay, and because of that it will be 1 divided by s minus a minus times of s plus a. Okay, so simply I can write 1 by 2, and this time it will be s plus a minus s plus a, and it will be s square minus a square, and s, this time s will be cancelled out, so it will become a divided by s square minus a square. Okay, so this was the formula, I mean this was the derivation of hyperbolic cosine and sine function. Any problem here? Tell me.
So
Yeah.
in the differential equation, when we were finding out that order of the differential equation for sine, and if the function comes inside the sine or cosine, we were using that expansion, isn't it? So if similarly, if it is coming in differential form is coming inside the hyperbolic function, can we do the similar thing?
It is an expansion, huh?
Yes, sir. If the differential equation come inside a trigonometric, similar to the trigonometric function, like in the hyperbolic function, then can we will be able to find out the order?
Yes, we can do that. We will solve one problem, okay? To solve the differential equation using the Laplace.
Okay, sir.
Okay? Yeah. We will solve, don't worry. And today only we will solve it. Okay? Now, we'll take another example. It was third. We'll take fourth example. And this was a little bit tricky, but it's not difficult. We have to find Laplace transformation of cos omega t and Laplace transformation of sin omega t. Okay, okay, so first I will write Laplace transformation of cos, so I will write as a subscript. Okay, subscript, that is LC, because we are finding the Laplace transformation of cos omega t, so that will be nothing but 0 to infinity cos omega t e raised to the power minus st dt. Okay, so here we have to use integration by parts formula. Okay, uh, I'm expecting that you know that. Okay, so if you want to if you want me to write that, I can write it. Okay, so this is the integration by parts formula. I will write it. So suppose if you want to integrate u v dx, then it will be u integral v dx. Okay, minus, you have to differentiate this, that is u dash, then you have to integrate this v dx, and after doing all those operations we have to again integrate it. So this formula is integration by parts formula. But yeah, we have to choose u and v cleverly, because sometimes maybe you are not able to integrate v. So in that situation what we will do is we will just swipe that. Okay, so maybe I know that we cannot integrate every function, but yeah, if it is possible then you can swap. Okay, after swapping you can check whether you can integrate it or not. Okay, so in this case what we will do, you can see that this is u and this is v. So cleverly we have to pick this as a u. So what we will do, I will write cos omega t, and this I will pick as a v. So what will be the integration? That will be e raised to the power minus st divided by minus s, and you have to put the limit minus 0 to infinity. Now we have to differentiate this. So what will be that differentiation? That will be minus omega cos, oh sorry, sine. It will be sine minus omega sine omega t. Okay, now we have to integrate, so that will be e raised to the power minus st divided by minus s, and we have to integrate it again. Okay, so I will write LC. Now here you can see that I will write minus 1 by S, and when you substitute this limit it will become 0 minus 1, okay, minus. Now you can see that there are 3 times negative sign, then again negative sign will come and it will become omega by S, and this will become 0 to infinity sine omega t e raised to the power minus st dt. Okay, so again I will write LC equal to 1 by S omega by S. Now you can see that this is nothing but the Laplace transformation of sine function. Okay, so instead of integrating it, I will just write LS. Okay, and I will name it as equation number 1. And similarly I will do the same operation with the Laplace transformation of sine function, and I will write 0 to infinity sine omega t e raised to the power minus st dt, and again I will apply integration by parts. Okay, so that will be, you can see that will be sine omega t divided by minus s e raised to the power minus st, limit 0 to infinity minus 0 to infinity, it will become w by minus s e raised to the power minus st cos omega t dt. Okay, so now you can see that when you substitute the limit it will become 0. Okay, and here it will become w by s, and it will be a Laplace transformation cosine function. Okay, so I will directly write LC. Okay, so LS equal to omega by S LC. Okay, now I will substitute equation 2 into 1. So you will get LC equal to 1 by S minus omega by S, and here you can see that was LS. So I will directly write omega by S LC. Okay, so when you move here it will become LC times 1 plus omega square S square equal to 1 by S. Okay, so here you will get what? S divided by S square plus omega square. This is the Laplace transformation of cosine omega t. Similarly, I can directly substitute to to find Laplace transformation of sine function. So you can see that S will be cancelled out. It will become omega divided by S square plus omega square. This was the second case. Fine. Any doubt here? Tell me.
No, sir.
Okay. Now let's take another example, that is polynomial. The case of polynomial, if ft equal to t. Okay. So in this case what will happen? Laplace transformation of t. This will be 0 to infinity t e raised to the power minus st dt. Okay, so Laplace transformation of t. Now can you tell me which function I should have to choose u and v, so that integral will be easy?
T as first function.
What?
T
T as what?
first function.
First function. Okay, t as u and this as a v. Okay, fine. So t e raised to the power minus st divided by minus s and 0 to infinity. Now we have to differentiate this. Okay, it seems like I am dividing it. Okay, but I am not dividing it. So the derivative of t will be simply 1 and e raised to the power minus st divided by minus s dt. Okay, and there will be a limit 0 to infinity. So Laplace transformation of t. Now you can see that what will be the derivative of this. I mean, by putting the integral, you will see that it will nothing but 0 minus 0. Okay, and this will be 1 by s. Now 0 to infinity e raised to the power minus st dt, and when you solve this integral, it will become 1 by s square. Okay, so this was the derivation of when ft is t. Okay, now This was the just basic derivation of simple functions. Now what we will do, I will just create a table so that we can use all those directly without solving. Okay, so in the first column I will write ft, and in the second column I will write Laplace transformation of ft, and that will be nothing but capital Fs. Okay, so I saw that when ft is 1, it was simply 1 by s. Okay, and when it was t, it was simply like 1 by s square. Okay, now I will generalize. What if t, if it is t raised to the power n, then it will be n factorial divided by s raised to the power n plus 1. Okay, okay, so now the next function is, we saw that e raised to the power at, and it was simply like 1 divided by s minus a. We'll move further. What if we have cos omega t, and it was simply s divided by s square plus a square. And for sin omega t, it was, oh, I wrote a, it should be omega. So it will be omega divided by s square plus omega square. Similarly for hyperbolic, cos h a t. Okay, so it should be s minus a. Okay, no, it should be s only, s divided by s square minus a square. And if it was hyperbolic sin at, then it will be a divided by s square minus a square. Now we will use properties. Okay, what if it is e raised to the power at cos omega t? Okay, so in this case it will be s minus a divided by s minus a raised to the power 2 plus omega square. It has simply shifted by a amount. You can see that at the case of omega cos omega t, it was s divided by s square plus a square, but when you multiply with e raised to the power at, it will be simply shifted by a amount. Okay, so that's why we call this as a shifting formula. Okay, I will talk about it. Okay, when e raised to the power at sin omega t, it will be simply what it should be? Tell me. If it is e raised to the power at sin omega t, what it should be?
Omega by s minus a square.
Yes, omega divided by s minus a raised to the power 2 plus omega square. Okay, okay, this was the table. You can use it directly. Okay, now we will use first shifting theorem. What it is that? First shifting theorem. Okay, it says if Laplace transformation of function f is fs, okay, then Laplace transformation by e raised to the power at times ft will be nothing but s minus a. Okay, this is called first shifting theorem. Similarly, in the case of inverse, if inverse Laplace of fs is ft, okay, then inverse Laplace of fs minus a will be simply e raised to the power at ft. Okay, so this was called first shifting theorem, and anywhere we can apply it simply. Okay, nothing we have to worry about it. So now we'll move to the transformation. transformation of derivative. Okay, so yeah, so from here, after getting to know the derivative of the Laplace transformation derivative, you can easily solve many kind of differential equation. Okay, so it says Laplace transformation of derivative of f is nothing but s times fs minus f0. Okay, here you have to be very careful. These two f are different. Okay, because this f0 is nothing but the initial condition. Okay, initial condition. Similarly, if we want to get Laplace transformation of double derivative, it will be s square fs minus s fs, okay, minus f dash 0. Okay, yeah, it's the wrong here, it should be f0. Okay, so this is the formula for the case of Laplace transformation of derivative. Okay, we can derive it very easily. Okay, nothing to worry about it. Suppose derive. Okay, derivation, let's derive it. Okay, suppose I want to get Laplace transformation of the derivative. What we will write? 0 to infinity f dash e raised to the power minus st dt. Okay, okay, now I will use the integration by parts. Okay, so what we will do, I will write this, I will treat this as a u and this as a v. So you can see that this will be e raised to the power minus st f dash dt. Okay, and after integrating I have to put the limit. Okay, now we have to differentiate this, so it will be minus times s e raised to the power minus st and integral of f dash dt, and there will be a outer integral dt, and here we have to put limit. Okay, so can you tell me what I can write here?
f of t.
Yes, so I can write e raised to the power st and integral of the derivative is nothing but the f. Okay, so 0 to infinity, and this time it should be plus 1, so 0 to infinity, and I can put outside as a s. So and here also you can see that it is the integral of derivative, so again it will be f e raised to the power minus st dt. Okay, so yeah, here you can see that when you substitute the limit, upper limit, it will be 0. Okay, but when you substitute the lower limit, this function will become 1 and this will be f0. Okay, plus s times, now you can see that this is nothing but the what, this is what, fs. Can you see it? So clearly I can write what it is, s of fs minus f0. This is the derivation of Laplace transformation of the derivative. Okay, now using this I can directly, not directly, with some small amount of work we can also get the Laplace transformation of the double derivative. Okay, so what I can write in the case of double derivative, I can simply write s of what, it is fs, no, fs for f. So I will write in the case of f double dash, it will be 0 to infinity f dash e raised to the power minus st dt. Okay, and here it will be f dash 0. It's fine or not? Can I write this? Tell me. Because fs, capital Fs is what? This. But in the case of double derivative, here at the place of fs, f will be f dash because it is a case of double derivative. Okay, so that's why I have written like this. So that will be second derivative, and now again we have to apply what, integration by part. So e raised to the power minus st, and when you integrate it, it will become f. again you have to put 0 to limit 0 to infinity minus, and again when you differentiate it, it will become s times e raised to the power minus st, and it will become f, okay, f dt, okay, minus f dash 0. Okay, so this will be f double dash, and now again you can see that it will become 0 minus what, f0, plus here again it will be limit is 0 to infinity, again it will be f of s minus f dash 0. So Laplace transformation of, now I will arrange everything, it will become s square fs minus, okay, minus s f0 minus f dash 0. So this is the derivation of Laplace transformation of second derivative. It's fine or not? Tell me.
This first step not understood.
This one.
Nine above.
Okay, this one.
This also.
Here I have used the same result which was derived previously, okay, this result, okay. So what did I do is I just replaced at the place of f dash as f double dash, okay. So this one will be as it is s, and we have to look into it at the place of fs. You can see that this is the fs in this case, but when you put f double dash, then at the place of f it will be f dash, because you can see that when it was single derivative, the derivative was reduced by 1 times. Can you see it? So similarly, in the case of second derivative, the derivative of f will be reduced by 1 time. That's why it's become first derivative. Fine. And here also you can see that at the place of f, it will be f dash 0. That's why I have written like it. Fine.
Okay, sir.
Yes. So this was the second derivative. Now I can generalize. If someone wants to derive, I will not derive it, it's just generalization. That is Sn Laplace transformation of ft minus s raised to the power n minus 1, f0 minus f s raised to the power n minus 2, f dash 0 minus minus minus, it will go on n minus 1 0. Okay, so this is the Laplace transformation of nth derivative. Fine. Fine or not? Tell me, any problem? Okay. Okay, so let's move to the Laplace transformation of integral of the function. Suppose you have some integration, okay? Okay, so suppose you have a function like this, 0 to t and f tau d tau, okay. You can see that it will be a function of time t when you integrate it with respect to tau, and when you substitute the limits, it will be a function of time t. So when you find the Laplace of this integral, it will be 1 divided by s f s, okay, where Laplace of ft equal to fs, okay, which means that suppose you have a function, okay, and you have the Laplace transformation of that function, that is fs, okay. Now you want to get the Laplace transformation of that function of integral, then that will be nothing but 1 by s fs. Fine. Let's solve one problem, then you will get it. Sixth Okay, find inverse of 1 divided by s times s square plus omega square. Okay, now I have to find inverse Laplace of inverse Laplace 1 divided by s times s square plus omega square. Okay, okay, so we know that the Laplace transformation of this function, that is what, sine omega t, that is nothing but omega divided by s square plus omega square. This thing I know. Now what will I do is I will just move this omega here. I can move it because it is a scalar, so this will be s square plus omega square. Okay, or you can also write the Laplace transformation of sine omega t divided by omega is nothing but 1 divided by s square plus omega square. Okay, now someone is asking what will be the inverse Laplace of this. So you can clearly see that this one is nothing but the 1 by s times of this, which means that inverse Laplace of 1 divided by s times s square plus omega square will be nothing but integral of 0 to t sine omega t divided by omega. It's fine or not? Tell me. And at the place of t I have to write tau. Tell me. It's fine or not? Any problem? Now what will I do? 1 by omega, it will be minus cos omega tau divided by omega 0 to t. Then it will be 1 by omega square minus times, when you substitute it, it will become cos omega t minus 1. Okay, so it will be 1 by omega square. Now it will be 1 minus cos omega t. So this will be the Laplace transformation of 1 divided by s times s square plus omega square. It's fine or not?
So, can you once again explain how that L inverse become integral 0 to t sine omega t by omega?
Okay, fine. From the previous definition you can see that suppose you have the Laplace transformation of ft, that is fs. Fine. Now someone is asking what will be the Laplace transformation of the integral of this function. Laplace transformation of the integral of this function, that is nothing but this, will be nothing but 1 divided by s times of fs. If you have Laplace transformation of ft, that is capital Fs, then the Laplace transformation of the integral will be 1 by s fs. Okay, here I know that Laplace transformation of sine omega t is nothing but the omega divided by s square plus omega square. Okay, then what did I do is I just move this omega here. Okay, since it is scalar I can write like this. So which means that the Laplace transformation of sine omega t divided by omega is nothing but this. Okay, now we'll go to the question, our problem. Here you can see that this one is fs for this ft. Okay, this one is fs for this ft. You can see that. Okay, this one is the fs for this ft. Now someone is asking what will be the inverse Laplace of this, which means that this is nothing but fs divided by s, which means that our new ft will be nothing but the integral of this. Okay, so you can clearly see that if I integrate it, which means that will be our Laplace transformation, inverse Laplace of that given function. It's fine. This is nothing but what? Fs divided by s. Okay, and this is nothing but ft, integral of 0 to t ft. It should be tau. Fine. Any problem?
No, sir.
Is it clear or not?
Yes, sir. Clear, sir.
Okay. Now again we will move to another problem that is very similar to this. We have to find inverse Laplace of 1 divided by s square plus omega square. Can someone tell me what could be the answer? What will be the answer? It will just integral of this, because now for this function this is our new fs. Okay, and this one is nothing but the 1 by s times of this fs, which means that our new ft is this, which means that we have to just integrate this function. It's clear or not? Tell me.
Yes, sir.
Yeah, it should be omega square. Okay, so 1 by omega square. Now the integral will be t minus sine omega tau divided by omega 0 to t. If you solve it, you will get what? T minus sine omega t divided by omega. This will be your answer. Okay, this will be the inverse Laplace of this function. Fine? Fine or not? Tell me.
Yes, sir.
Okay, let's solve
Yes, sir.
what? Are you saying something?
No, sir.
Okay, let's solve one initial value problem. Okay, of the differential equation y double dash minus y equal to t, and we have one initial condition, that is y0 equal to 1 and y dash 0 equal to 1. Okay, so to solve this differential equation, first we have to take Laplace on both sides. Okay, so the Laplace of y double dash minus Laplace of y equal to Laplace of t. Now from the previous derivation, I can write at the place of, since it is a Laplace transformation of the second order derivative, so I can write s fs. Since it is a y, so I will write capital Y minus s y0. Now it will be small y. Okay, because this y is different, minus y dash 0 minus ly. Ly is nothing but simply ys. Okay, because it's a Laplace transformation of y, so I will write ys, and this one is nothing but 1 by s square, because it is a Laplace transformation of t. So I will take ys as a common, so it will be s square minus 1, and s times, you can see y0 is 1 and y dash 0 is also 1, equal to 1 by s square. So I will write ys s square minus 1 divided by s square plus 1 plus s. Okay, now you can divide with s square minus 1 on both sides. So I can write s square minus 1, and when you divide with this function you will get 1 divided by s minus 1. Okay, by using the partial fraction, or you can directly write it what, s square minus 1 divided by s square minus 1 divided by s minus 1. At the place of 1 I can write this. So when you divide it, it will become 1 divided by s square minus 1 minus 1 divided by s square plus 1 divided by s minus 1. Now take inverse Laplace on both sides. Okay, take inverse Laplace. Okay, so when you take the inverse Laplace, so this time it will be yt. Fine, tell me. Fine, so at the place of this what I can write, tell me, inverse Laplace of 1 divided by s square minus 1, what will be the expression? Tell me what kind of ft it will be. Inverse transformation of inverse Laplace of 1 divided by s square minus 1, and at the place of this what it should be, and at the place of this what it should be, tell me. I'll go to the hyperbolic sine function. Okay, so you can see that it is a divided by s square minus a square, which means that at the place of a here it is 1. So this is nothing but sine hyperbolic t, and this will be what, 1 by t, and this will be what, e raised to the power minus t. So this is the differential equation, not t raised to the minus t, it will be simply t.
Sir, T, sir.
Yes.
Sir, there will be only T now.
Yeah, fine. So this is the oh yeah, it's a bit too t. Oh, sorry. Okay, so yt will be e raised to the power t plus sine ht minus t. So this is the solution of our differential equation. Okay, so the biggest advantage of using Laplace transformation to solve the differential equation is when the non-homogeneous part of the differential equation is unit function. Suppose you have a unit function, okay, on the right hand side, suppose it is a case of unit function. Okay, so from the very popular method previously, whatever we did it, we cannot solve from that. Okay, so here we have to take the advantage of Laplace transformation to solve the unit function kind of differential equation. So that is the biggest advantage of the Laplace transformation. Okay, now we will see the convolution. Okay, what is the convolution? Okay, so convolution says the Laplace transformation of f times z is not equal to Laplace transformation of f into Laplace transformation of g. Both are not same. Okay, but it says if h equal to, hs, if hs equal to fs into gs, okay, it is saying Laplace transformation of the product of two functions is not equal to the product of the Laplace transformation of those two functions. But if the transformed function in the terms of s is in the form of factor, then I can write ht, and that will be nothing but the convolution. And here you have to be very careful, it is not equal to ft times gt. Here the steric, it doesn't mean that it is a multiplication, but it is an integral of 0 to t f t g t minus tau. I am saying that if hs equal to fs into gs, and now you want to get what will be the ht. Okay, so to get the ht you have to solve this integral. Okay, you have to solve this integral to get ht. Okay, where ft is inverse Laplace of fs and gt is inverse Laplace of gs. Here steric is not the multiplication. Okay, it's just a notation. Fine, tell me, any problem here? Any problem?
Sir, what is this notation, sir?
This notation is just a convolution. Okay, it's just you can call convolution kind of multiplication. It's just a notation of the convolution. Okay, it's not a multiplication.
Sir, I don't know the convolution. What is convolution?
Yeah, the definition of convolution is this only. If you want to get the multiplication of two inverse Laplace function, then you have to solve this integral, and that integral is called convolution. Fine, this is the convolution. If you want to get the Laplace transformation of two Laplace function, two ft and gt, and you want to get what will be the small ht, then you have to solve this integral, then you will get ht. It's not simply like multiplication of those two functions, whatever I wrote it. Fine, let's take one example, then you will get it. Okay, suppose there is a function hs that is nothing but s divided by s minus a. Okay, and someone asks what will be the inverse Laplace of hs, what it should be. Okay, now you can see that if, I mean, you can assume let fs equal to 1 by s. Okay, and gs equal to 1 divided by s minus a. Okay, so here you can clearly see that hs is nothing but the fs multiply gs. Here it is a multiplication. Okay, here it is a multiplication. Now you can see that hs is nothing but the multiplication of fs and gs, and where fs is 1 by s and gs is 1 divided by s minus a. Now it is asking what will be the Laplace transformation of hs, or what is the ht. Okay, so it's very simple. We know that inverse Laplace of fs, that is nothing but the 1, and what will be the inverse Laplace, and that is ft. I will write it as a ft. And what will be the inverse Laplace of 1 divided by or gs? I will write gs, that is e raised to the power minus at, and that will be gt. Okay, now if I want to get ht, then it will be nothing but the convolution. Okay, and that is 0 to t f tau multiply g t minus tau d tau. Now solve the integral simply. What is the f tau? 1. What is g t minus tau? So e raised to the power minus a, and at the place of t I will write t minus tau d tau. Okay, so Here you can see that the variable is tau, so I will simply write e raised to the power minus at outside 0 to t e raised to the power minus tau d tau. Okay, so e raised to the power minus at, and here it should be a. So e raised to the power minus a tau divided by minus a and 0 to t, so e raised to the power minus at minus a, and when you put the limit, it will be e raised to the power minus, what it should be, at, no, at minus 1. Tell me, any problem here? Oh, it should be plus. So 1 divided by minus a, and here it will be 1 minus e raised to the power minus at. Now it will be e raised to the power minus at minus 1 divided by a. So this is your ht. Any problem? Am I making any mistake in the integration? That is minus at plus a tau minus at e raised to the power a tau. Yes, it's correct. So this is the ht, you can see it. So this is the way you can find inverse Laplace of this. Any problem here? Tell me. It should be plus, no? It should be plus here. Yeah, now it's correct. Yeah, tell me, what is the doubt here? Any doubt?
No, sir.
It's clear. Simply you have to integrate. First you have to find fs, then gs, and you have to find ft and gt, and just write in this form and integrate it. Simple. This is your ht, small ht, and that is nothing but the inverse Laplace of 1 divided by s times s minus a. This is your ht. This is one example for the convolution. Okay, let's take one more example, then if you have any doubt, let hs equal to 1 divided by s square plus omega square square. Okay, so it's clear that now I have to find what will be the inverse Laplace of hs. Okay, what it should be. Okay, so it's clear that you can see that if I assuming fs as 1 divided by s square plus omega square, and also I am assuming gs equal to 1 divided by s square plus omega square, and when you multiply it, it will become hs. Okay, clearly hs equal to Fs multiply Gs. Now you have to get what is Ft. Okay, for this what will be the Ft, and this is nothing but the sine omega t divided by omega, and this one is also same, so I will write gt equal to sine omega t divided by omega. Now I have to get ht, and that is the convolution. That's what we have to get. L inverse hs is nothing but the ht we have to get it. So what we will do, I will do convolution, and that will be integral 0 to t. Okay, sine omega tau divided by omega multiply sine omega t minus tau divided by omega d tau. Okay, so that will be 1 divided by omega square 0 to t sine omega tau multiply sine omega t minus tau d tau. And when you apply one trigonometric function formula of sine A into sine B, that's what you have to apply. That's formula you have to apply here. Okay, we know that 2 sine A into sine B will be cos A minus B. Okay, cos A minus B minus, here it should be minus cos A plus B. This formula you have to apply here. So 1 divided by 2 omega square. Now you can see when you apply it, it will become 0 to t cos omega tau minus omega t plus omega tau. This one minus cos A plus B, cos A plus B, so it will become cos omega t d tau. Okay, and when you solve it, I will not solve here, you will get 1 divided by 2 omega square minus t cos omega t plus sine omega t divided by omega. So this is your ht, and that is nothing but the inverse Laplace of 1 divided by s square plus omega square raised to the power 2. Fine? Tell me. So these two are example of convolution. Let's go to the integral of the transformation. Integral. Okay, if you have, suppose if Laplace transformation of L of ft is fs, then it says Laplace transformation of ft divided by t will be integral of s to infinity. It should be s to infinity of f. Here I am writing s bar because variable should be different, because I have already put the limit in the form of that. So yeah, so it is saying that suppose Laplace transformation of ft equal to fs. Okay, and you want to get what will be the Laplace transformation of ft divided by t, then you have to integrate it, then you will get it. Or in inverse Laplace form, you can write inverse Laplace of s to infinity f s bar ds bar will be ft by t. Okay, for example, I need the Laplace transformation of sine t by t. What will you do? In the case of Laplace transformation of sine t by t, then you have to integrate s to infinity, and you know that Laplace transformation of sine t is nothing but the 1 divided by s square plus a square, and I will write s bar. ds bar. Now just integrate it and you will get Laplace transformation of sine t by t. Okay, so that's why it is also very useful. Okay, I think in GATE exam they have already asked this problem. Any problem, any doubt here, tell me. Any problem? Tell me.
No, sir.
No. Okay, now let's move to the unit step function. Unit step function, and this one is also called Heaviside function. And from the definition it says the value of this will be 1 when t is greater or equal to a, and the value of this will be 0 when t is less than a. Okay, and from the graph you can also see that this kind of function you will see in the case of it is a ut, but in the case of u of t minus a, from a the value will be 1. Okay, when time t is greater or equal to a, the value of ut minus a will be 1, otherwise it will be 0. Okay, so now I want to get what will be the Laplace transformation of this unit step function. Okay, so it's very easy, just integral. Now I will break this integral 0 to 1, or not 0 to 1, 0 to a, because from a that integral is breaking, plus a to infinity ut minus a e raised to the power minus st dt. Now you can see that in this interval 0 to a the value is 0, so this one will become 0 and a to infinity, and in this interval when a is greater or equal to a, this ut minus a will become 1 times e raised to the power minus st dt. So when you integrate it you will get e raised to the power minus as divided by s. So this will be a Laplace transformation of unit step function. Okay, suppose you have a differential equation something like this. Okay, so in this case you can solve this kind of using this kind of Laplace transformation you can solve this kind of differential equation. Okay, now our the last topic, and I think GATE has not asked this problem, but in future they may ask in 1 marks question. Okay, so Laplace transformation of periodic function. Okay, what is the periodic function, tell me, what is the periodic function?
So repeat in every interval.
Okay, in the form of function, how can I write it?
Sine function.
No, no,
Tan
just a
function
general
cos
function, just general function. I will write ft plus capital T will be simply ft. Okay, where t is the time period, where t is the period of ft. Okay, so it is saying that if you want to get Laplace transformation of this kind of periodic function, then it will be simply 0 to capital T ft e raised to the power minus st dt divided by 1 minus e raised to the power minus st. GATE has not asked yet, but they can ask, okay, in just 1 marks question, which one of the following is a correct. Okay, okay, so let's derive it. It's very simple, it's not very lengthy. Let's derive it. So 0 to infinity ft e raised to the power minus st dt. So yeah, okay, so what will I do is I will just break this integral in this form. Okay, and so on, it will go up to infinity. Okay, now what will I do is I will pick this integral and I will see what is the behavior of this. Okay, I will leave this as it is, but I will solve this integral. Okay, and I will solve this by using one substitution. And what is that substitution? I will substitute u equal to t minus capital T, and when you substitute it, it will become du equal to dt. Okay, this variable will become dt. Yeah, at the place of dt I can write f, and at the place of t I will write u plus capital T e raised to the power minus s, and at the place of t I will write u plus capital T and du equal to dt. Oh, sorry, dt equal to du. Okay, now when you substitute t as a capital T, it will become 0, and when you substitute small t as a capital 2t, it will become capital T. Now you can see that the limit of these two becomes same. Okay, and we also know that fu plus t is nothing but fu, because it is a periodic function. Okay, so e raised to the power, now I can write, because either here u is a variable. Okay, so I will write like this. Okay, this one is not a part of this integrand, because here the variable is u and it is a capital T. Okay, so I can simplify this integral into this form. Similarly, if I simplify this integral, okay, and this time I will write small u equal to t minus 2t. I will substitute this. Okay, and this time that integral become 0 to capital T, f will become u plus 2t, and e equal to minus su du, and that outside will be e raised to the power minus 2s capital T. Okay, and it will be same as it is. Okay, it will go on. So when I write 0 to infinity ft e raised to the power minus st dt, I can write 0 to t 0 to t ft. Okay, here it should be ft e raised to the power minus st dt plus e raised to the power minus s capital T 0 to t ft e raised to the power minus st dt plus e raised to the power minus 2st 0 to t ft e raised to the power minus st dt, and so on. Okay, Now you can see that all these terms, this term all same. So I will write 0 to capital T ft e raised to the power minus st dt. Okay, and this one is nothing but 1 plus e raised to the power minus s capital T plus e raised to the power minus 2s capital T plus e raised to the power minus 3s capital T, and so on. Okay, now can you tell me what is this? What is this? This is a series, no? What kind of series is this? This, yeah, tell me.
Geometric progression.
Yeah, geometric progression, and it is an infinite geometric progression. Okay, this is a GP, and here the first term is 1 and the common ratio in this case it is a GP. Okay, and where a is 1 and common ratio is simply this e raised to the power minus s capital T, and we know that sum of the infinite geometric series is 1 divided by 1 minus r. Okay, so I will write 1 divided by 1 minus e raised to the power minus s capital T. Okay, now you got it. What will be the Laplace transformation of ft? That will be 0 to capital T ft e raised to the power minus st dt divided by 1 minus e raised to the power minus s capital T. So this is the derivation. Any problem here? Tell me. It's fine or not?
Yes, sir.
Yeah, so these are all about Laplace transformation. Today's lecture is over. Okay, in the next lecture probably I will start. Actually I have already given the schedule. Next time you will see in that portal, you will see the topic wise what will I teach in the next week. Fine. Okay, so today's lecture is
And
over.
what's up?
Yeah.
Can you go? Are you going to take complex variables topic?
What complex variable you need?